Let's continue our discussion in leaderless replication. And we'll begin with talking about concurrent writes. So, recall that last time we talked about strict quorums and how if you have read and write acknowledgements greater than the total number of shards or a total number of replicas, you guarantee that your value is going to be consistent, right? But that only works for the case where you have one client, or if one client is writing and the other client is reading. In the case where we have multiple clients writing to this database cluster, if the database receives concurrent writes from client 1 and client 2, it's essentially guaranteed to have a conflict. So concurrent writes leads to conflict even with strict quorum. But if we simply overwrite the value where the write request is received, we will leave the database in permanent inconsistency. And you can see this by just thinking about the fact that if request 1 arrives before request 2 on node 1, node 1 is going to take request 2, right? And if it arrives later on node 2, then on node 2, I'll see request 1 as the final value. So the database has no way of determining which request should go before the other if two requests are concurrent. So we need a way to ensure that we have eventual consistency. And the first way we do this is by ensuring that the last write wins. Last write wins essentially discard the concurrent writes by appending a timestamp to all of the requests. So if you have a timestamp appended, then each node can easily tell which request came first and which one came second, even if the later request arrived before the the first request, right? But the trade-off is that we gain eventual consistency, but we have durability loss. And the reason why we have durability loss, let me give an example here. So if 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 we have client A here writing to this cluster, we go here, we write 1, and we write 2, and we write 3, right? And the response is, so response from each shard, each replica is okay. So A thinks that the request has been successfully written. And at the same time, a request from B is received at all of these nodes. But because B landed after A, and the value of B has overwritten the value written by A, right? So you can see how here, so here we'll have, so let me do it this way. Let's say something like this, right? And we're writing, let's say we write B, B, and B, right? Here we have A, A, and A. The final result of our database cluster will just be B across the board. Right, we append, see, we write B when t equal to, let's say, 1, and we write A when t equal to 0, right? So here we're going to say t the database now value is b, final value. The final value is b, but you could see that A successfully wrote its value into the database, but the next time when it queries, it's going to get B, and we silently dropped A, and we lost durability. So this is the trade-off when we use last write wins. So how do we detect concurrency and how do we resolve it? We define that A happens before B if B knows about A or is dependent on A. Okay. But they are concurrent if neither happens before or after, right? If either A, so they're concurrent if neither happens before the other, right? So we're not unable to determine which came first. They happen at the same time. So there are three scenarios when a request, when the requests are sent from two sources. Either our request A happens before request B, or B happens before A, right? Or they're concurrent. And the exact time does not matter as long as A and B are unaware of each other. This is the definition of the concurrency model in distributed systems. So the exact time does not matter. It could be days, it could be weeks, as long as B and A are not aware of each other and are not dependent on each other.